Okay, our first problem is to compute a sample size. And we have, we're comparing groups, 6-hour patching to full-time patching. And the subject will be measured at baseline and 4 months. So we have an analysis of covariance type design. We're going to consider a difference of one line between groups to be clinically relevant. One line equals 0.1 logmar. Each letter is 0.02 logmars. 5 letters to a line, 0.1 logmar. The standard deviation from previous literature is shown to be 0.18 logmar. The correlation between baseline and follow-up at 4 months is estimated to be R equals 0.7. What is the effect size to find a one-line difference? Well, our standard deviation is 0.18. We want to find a one-line difference, which is 0.1. 1 divided by 0.1 divided by 0.18 is 0.5556. So our answer is 0.5556. Now, in case people did not get this, I gave you an effect size to use, 0.5, which is actually kind of close. Notice here I have modified the effect size to equal 0.556 because things are automatically changed. The whole table changes. Now we wanted to find an alpha of 0.05 with a power of 0.9 and a correlation of 0.7 with an effect size of 0.5. That's 43 subjects. If we had used the actual one we were looking for, it would be 35. But 43 subjects is the answer to the second part of this. 43 per group. Okay, now we're going to go to question 2. We're going to use the longitudinal vision data set. And we are going to be interested in spherical equivalence and relative peripheral refraction for myopes only. And so first, let's just take a look at a box plot of spherical equivalent by this variable called init years. Init years are the years observed relative to the first year the subject was diagnosed myopic. So let's go where? Okay, let's find our okay, let's go to our SPSS. I've already loaded up the longitudinal file. And we're going to, it's asking for a box plot of spherical equivalent by init years. So graphs, legacy, box plot, sample, define. We have spherical equivalent by init years. And here is our chart. Now, the thing that's kind of interesting about this, now, init years, 0 is the year they were diagnosed myopic. So everybody has this as the baseline reference point for the myopes. I should say we needed to select for only myopes, although not really because only myopes have init years. But if we select for last ref status 5 equals 1, that just gives us normal myopes. If we don't do that, we'll get the extreme myopes too, and we don't really want those in here. I'd like to point out this. People are starting out a little hyperopic, and they're on their way towards myopia, and then the year they become diagnosed, that's kind of a rapid advance, dropping off the cliff, and then it continues to become more myopic. All right, but so what you are to do is to insert this into here, and there we go. Now let's look at a box plot with peripheral refraction, relative peripheral refraction. That's rel pref act, graphs, legacy, box plot, simple, define, get rid of that one, replace it with that one, and we're good to go. And here we see quite a different relationship. Now, it's helpful to interpret this graph. Oops, I should have done that before I copied it. It's helpful to interpret this graph by adding a horizontal bar. Notice it comes up at 1. We change that to 0. And now we have a 0 through there. And we can see that before the person becomes myopic, they tend to have a negative value, which interestingly enough is relative myopic defocus. And after you're myopic, you have relative hyperopic defocus, as defined by the measures. I think this is unusual. Generally speaking, Earl Smith and everybody says it's hyperopic defocus that causes myopia, but you can see that's not the condition if the measure is correct. All right, let's close the. Let's copy this. Copy chart. Let's put it in here. Delete that. Paste. Okay, try again. Copy. Paste. All right. Now, some of the data are pretty sparse, so we need to select init years that are -4 through +3 years. So I didn't actually show you the first data that we did. And actually what I've shown you here is my data set was already truncated from before, so I only show you -4. Your data will have had years that go from -7 and on up to like +6 or something. We're just doing this abbreviated part here. So let's just review data selection, and our if statement is last refractive status 5 equals 1. That's myopes only. And init years greater than or equal to -4, and init years less than or equal to 3. And so that statement will select only relevant people. if you had looked on the data set, you would have seen that I gave you those filters. Okay. So now that we've done that, after we've selected it, we want to run a frequency analysis. Now, the advantage of doing this is it will give us sample sizes for later on. So we have init years relative to myopia. Let's hit OK. We get a frequency. We're going to copy that into here. And then we are to run a mixed model analysis looking at the effect of init year on relative peripheral refraction. And we're going to run it 3 times, once using unstructured, once AR1, and once compound symmetry. So let's do that. We have analyze, mixed models, linear. We're going to start with unstructured. Down here, we have our ID. We have init years for the repeated. We have a covariance structure. That we're going to get rid of that covariate. And we have relative peripheral refraction. We have init years. Our model has init years. Our statistics. We don't really need parameter estimates because we're not doing any continuous variables. We can test them, not really using that, but it doesn't hurt anything. Oh, also notice I had included descriptive statistics, but you don't really need that either. That can only probably confuse you if you had done that, but you could. Doesn't hurt anything. And we have our estimated marginal means, init years, and we compare them to each other. Okay. I'd like to point out something here. We get a warning. Warnings are not good. The validity of the model is uncertain. Let's come down here. We look at our information criterion. It's 2606. Why did we not fit? If we come down here and we look at the estimates, actually if we looked at the pair comparisons, we will see as we go down this list, we have, well, honestly, I don't know why it didn't work, because it's got everything filled in. Well, it didn't like it, so we shouldn't use it. Oh, here we go. It's all that. Oh, it's in, well, that's the descriptive statistics. I don't care about those. Information criteria. Ah, here it is. In the estimates of covariance parameters. Now I ask you to copy those in. So we're going to do that right here. Notice these blanks and 0 standard errors. That's from sparse data and these correlations. There weren't too many people that had the highest and lowest time in the program. It just didn't last that long. So it doesn't fit that well. All right, so now it asks for an autoregressive mixed model, linear, autoregressive. Everything else stays the same. So basically, because that didn't converge, we don't really consider this as a viable one. So we look at the covariance structure for that. We get this little thing. We come down here, we insert it, paste it, and then we go to the next one, compound symmetry, analyze, mixed model, linear, compound symmetry, continue. Okay. And we look at the estimates. That's that. Copy. Paste. All right. Now we've done those and we've gotten all three. Which covariance structure was best and why? Well, we're not going to consider, actually it's the next question, why should you not consider the unstructured matrix? It did not converge. So which covariance structure was best? So that leaves the last two. Our information criteria, Ake-Ike's 2650. This is the compound symmetry one. And the other is 27. So 2716. So 2650 is better than 2615. It's also a simpler model. Well, not really. There's just two parameters in each one. But compound symmetry worked better. The Ake-Ike's IC was better. Model was, oh no, it's not simpler. Stop saying that. Okay. Why was AR1 a reasonable structure to consider? Well, let's look at the structure of AR1. So what this says is variables are correlated, and like if you think of this as visit 1, 2, 3, 4, visit 1 and 2, the estimate is just row correlation. At 1 versus 3, it's squared, so it's a smaller correlation and a smaller correlation. So first order autoregressive works because it says that visits that are closer together are correlated more to each other. That would make sense. You would kind of expect that. It turns out, though, that the compound symmetry, which assumes equal variances, that there is not that relationship, actually works better. So I was kind of surprised at that, but hey, that's the way it was. Visits closer together are more correlated. Using the variance from the best covariance structure, create an Excel column chart with estimated mean errors with 84% confidence interval. So we're going to copy our compound symmetry group into an Excel worksheet. And here we have it. There's that point 28. This is the covariance structure for compound symmetry. Here are our estimates that we copy from the output. And here are our frequencies that we copied when we ran the frequency program. And what I did was I copied these little guys and I put them up here. And then for compound symmetry, our error term is going to be the square, we're going to compute the standard deviation. And then because our sample sizes are different, we need to compute the standard error separate for each one. So this is the square root of the sample size times the standard error. Actually, this isn't the one we used. I was looking at the similarities between that. It's this one that we're doing. We have the standard error, the standard deviation, times the square root of n gives us the standard error. Get rid of that. I was playing around a little bit. So we need to do equals t inverse times 0.16. Degrees of freedom are n minus 1. And then we take that, multiply the t times the SE to get that. And those are our, this is our plus or minus right here. So let's do a graph, year, mean, insert, chart. Okay. Get rid of that little guy. Well, let's see, design, add a chart element, error bars, custom, specify, the upper is that, the lower is that. Okay. Now, let's just compare this for a moment. Well, let's do our exam. Copy. And why is it using the variance? Okay, there's our chart. We could label it in years and peripheral refractive error. Now you can see these don't overlap 0, but really we could do the test if we had used error bars at 95% rather than, because there's only, here we use 84 because we're comparing two different estimates, two samples. This, if we compare it against 0, it's one sample estimate against a fixed value of 0, and we would do a 95% confidence interval. But you can see these guys are, even if you added a little bit to it, they're going to be different from 0 in a myopic defocus kind of way. I mean, the next question asks, consider vision science lectures you've attended and reflect on the results. Well, the results are that this is myopic defocus before they're myopic, and it's supposed to be hyperopic defocus. So I would question, first of all, that could be true, and when you're doing near work, for example, and you're bringing the book in close, even though when you're doing a infinite target or whatever target you're doing in a Grand Seiko way of measuring refraction, it could be that that relative peripheral refraction does not reflect myopic and hyperopic defocus, or it does, and when you are in a situation where you're reading or something, you're moving yourself close to the text and you're going hyperopic defocus more in this case. I don't know why that is, but it's just an interesting contradiction. Now, after you've become myopic, This makes a lot of sense. You are now having this hyperopic defocus. It's interesting to speculate on the fact that it may be that people have gotten their hyperopic defocus thought by looking at kids that are already myopic. Although I would argue against that because of Smith's studies with his Jim Smith and other people have all shown hyperopic defocus seems to be the what causes, or is associated anyway, with myopia progression. All right, so I've given you that little talk, and that's what you would fill in there. And that's basically it.